The telescope, this powerful instrument, has captured images that are not only visually stunning but also deeply thought-provoking for scientists around the world. These images are challenging long-held beliefs about the universe's origin, structure, and expansion, causing a stir in the scientific community and reigniting debates that have persisted for decades. These aren't just beautiful cosmic photographs to admire, they are windows into the deepest questions we have ever asked. Among the most impactful of these findings is an image that has sparked renewed discussion among astrophysicists. This image, more than just a remarkable photograph, may help resolve some of the deepest questions about the cosmos. It has provided new data that contradicts certain aspects of the Big Bang theory, which has dominated cosmological thinking for over a century. The Big Bang theory posits that the universe began approximately 13.8 billion years ago from an extremely hot, dense state and has been expanding ever since. It remains one of the most influential frameworks for understanding the universe's origin. Yet the new observations being collected and analyzed are forcing scientists to revisit some of its core assumptions. One major focus of this ongoing discussion is the age of the universe and the rate at which it is expanding, two elements that are critical to our overall model of how the cosmos operates. For years, scientists have relied on a value known as the Hubble constant, a measure of the universe's expansion rate, to determine both the size and age of the universe. But calculating this constant has proven far more complex than originally thought. There are two primary methods used to estimate the Hubble constant, and unfortunately, the results derived from these methods don't align. This discrepancy has led to one of the most intriguing puzzles in modern astrophysics. The first method is based on local measurements. This approach uses what astronomers refer to as standard candles, astronomical objects like Cepheid variable stars and Type Ia supernovae, that have a known intrinsic brightness. By comparing their observed brightness to their known luminosity, astronomers can determine how far away they are. Then, by measuring how fast these objects are moving away from us, scientists can calculate the Hubble constant. These local measurements suggest that the universe is expanding faster than previously believed. The second method involves observations from the early universe. Scientists analyze the cosmic microwave background, or CMB, which is the afterglow of the Big Bang. This radiation has been traveling through space since the universe was only about 380,000 years old. Discovered in the 1960s, the CMB has been instrumental in shaping our understanding of the early cosmos. By examining the minute fluctuations in temperature and polarization within this radiation, cosmologists can infer the universe's age and rate of expansion at that time. However, there's a serious issue, one that has only grown more pressing. The results from local measurements and those from the CMB do not match. This discrepancy is known as the Hubble tension, and it's become one of the most significant unsolved problems in astrophysics today. If both measurement methods are valid, and there's reason to believe they are, it suggests that there is a fundamental aspect of the universe we are missing or misunderstanding. Scientists have worked tirelessly to determine whether the disagreement stems from observational errors, misinterpretations, or a deeper issue within our theoretical framework. This is where the James Webb Space Telescope enters the picture. With its advanced infrared capabilities and its ability to observe distant objects with unmatched clarity, the telescope allows us to peer further into the universe than ever before. Scientists hoped its data would help reconcile the conflicting measurements and refine our understanding of the Hubble constant. But instead, the first wave of data from Webb has only deepened the mystery. The results continue to diverge from what was expected based on previous models, suggesting that our understanding of cosmic expansion may require a fundamental overhaul. Rather than closing the gap between the CMB measurements and the local observations, Webb's insights are widening it. These findings are prompting scientists to think beyond established theories. The discrepancies might point toward new physics, undiscovered particles or forces that could reshape our understanding of space and time. They may also indicate that our current model of dark energy, the mysterious force believed to be accelerating the expansion of the universe, needs to be reconsidered. Every time we uncover new data, it pushes the boundaries of what we know and forces us to reassess our theories. Take, for example, the discovery of the cosmic microwave background in 1965, which provided compelling evidence for the Big Bang theory. Before that discovery, many scientists believed the universe would continue expanding forever at a steady rate. However, the observation of accelerated expansion in the late 1990s introduced the concept of dark energy, a force that acts in opposition to gravity and causes the universe to expand faster over time. This was a major turning point, demonstrating that even the most trusted theories must adapt when faced with new evidence. Today, scientists are dealing with similar challenges. Each discovery raises new questions and forces a comparison with previous knowledge. The process may be complex, full of uncertainty and revision, but it is also incredibly rewarding. Confronting problems like the Hubble tension compels researchers to develop better tools, refine their methods, and explore new ideas about the universe's past, present, and future. The questions surrounding the Hubble constant aren't just abstract puzzles. They influence everything from how we model galaxies to how we predict the ultimate fate of the cosmos. Another crucial concept closely tied to Hubble tension is what scientists refer to as sigma tension. This deals with how matter is distributed throughout the universe. When astronomers observe space, they see that galaxies aren't spread out evenly. Some regions are packed with galaxy clusters, while others are nearly empty. Understanding why this is the case can help us trace the universe's evolution over billions of years. To investigate this, scientists use a technique called gravitational lensing. This occurs when massive objects, like galaxy clusters, bend the light from even more distant galaxies behind them. This bending effect helps astronomers detect dark matter, an invisible form of matter that doesn't emit or absorb light. It reveals itself only through its gravitational pull. Gravitational lensing gives scientists a way to map the distribution of dark matter across the universe. They also turn again to the CMB, which contains information about the earliest fluctuations in matter after the Big Bang. However, a new problem has emerged here too. The irregularities predicted by studying the CMB do not match the large-scale structures observed in the present-day universe. In particular, the gravitational patterns we see now suggest that matter was less evenly distributed in the early universe than the CMB data implies. This inconsistency again points toward the possibility that there's something missing in our current understanding. Perhaps it's something about the behavior or nature of dark matter that we have yet to grasp. A research team led by Adam Rees explored whether the differences in measurements could be attributed to errors in the Hubble Space Telescope's data. But when they used the James Webb Space Telescope to check, they saw the same inconsistencies. This raises an even more concerning possibility, that there is a fundamental flaw in how we interpret cosmic observations. In an interview with an American astronomical journal, Rees remarked that somewhere between these two methods, local and early universe measurements, there may lie a key misunderstanding that needs to be uncovered. Thanks to the James Webb Telescope's precise infrared imaging, researchers are now able to observe objects at much greater distances with improved accuracy. These capabilities help refine the measurement of cosmic distances and further highlight the discrepancies between various methods. But the new clarity has not brought harmony to the data, it has only made the contradictions clearer. Instead of convergence, we're seeing sharper divergence. Meanwhile, the mysteries of dark matter and dark energy remain at the heart of modern cosmology. These two elements are thought to make up most of the universe's mass-energy content. Yet their true nature remains elusive. While black holes were once thought to account for many unexplained gravitational phenomena, more attention is now being directed toward how dark matter and dark energy could be influencing the behavior of galaxies and cosmic structures. Our search for answers continues, and each new discovery reveals how much we still don't know. But that's what makes science, and cosmology in particular, so powerful. It's an ever-evolving journey, where new tools like the James Webb Space Telescope not only provide data but also inspire new questions. The universe is vast, and its secrets are slowly coming into focus. But with each answer comes a new mystery to explore. As cosmologists struggle to untangle these mounting discrepancies, the pressure to revise our understanding of the universe is intensifying. It's not merely a matter of mismatched numbers. It's a potential indicator that our very model of the universe may be incomplete or even fundamentally flawed. Theories built over decades, relying on the Big Bang, dark matter, and dark energy, are being put under the microscope once again. The James Webb Space Telescope, originally launched to deepen our understanding of the early universe, has instead thrown us a scientific curveball. Its unmatched resolution and ability to observe galaxies billions of light-years away are not just confirming old theories, they're shattering our confidence in them. Take, for instance, Webb's ability to peer back in time by detecting light from the earliest galaxies ever formed. These galaxies should, according to prevailing models, be small, chaotic, and in early stages of formation. But the telescope is finding surprisingly mature, massive, and structured galaxies at epochs where they should not yet exist. This has stunned astronomers. If large galaxies were already formed just a few 100 million years after the Big Bang, then something is off with our timeline of cosmic evolution. Either galaxies form far faster than we believed, or the Big Bang timeline itself needs recalibrating. These results not only contradict existing cosmological simulations, but also imply that matter may have clumped together more efficiently in the early universe than our physics currently allows. This brings us back to the heart of the problem. What do we really know about the fundamental forces shaping the universe? Dark matter and dark energy are terms we use as placeholders for phenomena we don't yet fully understand. Dark matter, for instance, is known to account for roughly 27% of the universe's total mass energy content. It does not interact with electromagnetic radiation, which means we cannot see or directly detect it with telescopes. Its presence is inferred solely by the gravitational effects it has on visible matter. For example, galaxies rotate faster than they should based on the mass we can observe. This excess rotational speed is attributed to the gravitational influence of dark matter. But what if our assumptions about dark matter are wrong? Several theories attempt to modify gravity itself rather than invoking an unseen form of matter. One of these, known as modified Newtonian dynamics, suggests that the laws of gravity may behave differently at galactic scales. Another bold framework, known as emergent gravity, proposes that gravity is not a fundamental force but an emergent phenomenon from quantum entanglement and thermodynamics. While these theories remain controversial, the growing contradictions in observational data, especially with sigma tension and gravitational lensing, are giving them renewed consideration. Dark energy is even more mysterious. Accounting for about 68% of the universe's energy content, it is responsible for the observed acceleration of cosmic expansion. But what is it, really? Is it a property of space itself, as Einstein once proposed with his cosmological constant? Or is it something more dynamic, a new field permeating the universe that changes over time? Some speculative models even suggest that dark energy may decay or evolve, potentially altering the fate of the universe itself. In one such model, known as phantom energy, dark energy becomes so dominant that it eventually tears apart galaxies, stars, planets, and even atoms in a hypothetical Big Rip. The James Webb Space Telescope offers an unprecedented opportunity to test these ideas. By observing the distribution of galaxies across vast cosmic distances and timescales, it enables scientists to map how structures formed and evolved. If dark energy behaves differently than expected over time, these maps should reflect that deviation. Early results are inconclusive but suggest that our cosmic expansion history might not be as smooth or uniform as we once thought. In fact, Webb's high-resolution spectroscopy may even allow for direct tests of fundamental constants, such as the fine structure constant, to see if the laws of physics themselves have varied over billions of years. Meanwhile, sigma tension continues to challenge the idea that the universe has evolved linearly from the early conditions recorded in the CMB. If gravitational lensing and galaxy surveys show a more clumpy universe than predicted, it could mean that either dark matter behaves differently than expected, or some previously unknown process amplified the formation of structure. Some researchers have proposed interactions between dark matter and dark energy, or even entirely new particle families, to explain these anomalies. Others suggest the universe may contain extra dimensions, curled-up spatial dimensions that affect gravity's strength on cosmological scales. Then there's the possibility that the universe we observe is just a small part of a much larger multiverse. In some versions of string theory and quantum cosmology, our universe is one bubble in a vast multiverse where different physical laws may apply. If so, the values we measure, like the Hubble constant, could be local phenomena, not universal ones. While speculative, this idea could help explain why our universe seems so finely tuned for life, a mystery known as the anthropic principle. The James Webb Telescope won't directly observe other universes, of course, but by pushing the boundaries of our observable cosmos, it may offer indirect clues. In the face of so many unknowns, the importance of continued observation cannot be overstated. The JWST isn't working alone. Its data is being compared and combined with results from other observatories such as the Atacama Cosmology Telescope, the Sloan Digital Sky Survey, and the upcoming Nancy Grace Roman Space Telescope. Together, they form a network of cosmic detectives, searching for patterns that could crack open the secrets of dark energy, dark matter, and the underlying geometry of space-time. Another area where Webb is making transformative contributions is in the study of reionization, the period in the early universe when the first stars and galaxies ionized the intergalactic medium. This epoch, which occurred around 400 million years after the Big Bang, is crucial for understanding how light spread throughout the cosmos. Webb is now detecting galaxies from this era with such clarity that scientists can measure their chemical composition, star formation rates, and even black hole activity. These findings may eventually offer indirect insights into whether early energy outputs could have influenced the formation of structure in ways not previously understood. The telescope is also revealing an unexpected level of complexity in planetary systems beyond our own. By analyzing the atmospheres of exoplanets, it is contributing to our understanding of planetary formation, evolution, and even the potential for life elsewhere. While this seems unrelated to cosmology at first glance, it actually ties into a deeper question. Is our universe typical, or is it special? If life-friendly conditions are common, it could suggest that the universe has properties deliberately or naturally tuned for complexity. If they are rare, it may point us back to unique circumstances in the evolution of our galaxy and solar system. Perhaps most importantly, the James Webb Space Telescope is proving something far greater than any single scientific conclusion. It is demonstrating the limits of human knowledge and the boundless potential for discovery.